Today I have a function to show you. This function, it's pretty harmless, not much. I've not even given it a definition yet, so um let's say maybe this function prints out something like hello. Pretty simple function, right? Now, what if I call this function? What do you think is gonna happen? Well, logically, if I run this so that the IPYNB understands what do stuff is, and I run do stuff, it's gonna tell me hello. But what if I include do stuff inside of the declaration of what do stuff means, inside of kind of what the code is required to do when do stuff is called? This is effectively telling Python, when I call do stuff, well, print hello and then call do stuff, which prints hello and then calls do stuff. Well, if I hit this, nothing happens. But that's because it just exists. This instruction just exists, but nothing is making the first domino topple over. So what if I just call do stuff for fun? Whoops, sorry, that's the function itself. Whoa, what is this? That's not making a lot of sense. Okay, this is crazy. My RAM's probably spiking. Kernel needs to be interrupted. Something is going wrong. If this was an actual computing exam, I'm completely cooked. Oh, whoa, what's this error? I've never seen this before. Maximum recursion depth exceeded while calling a Python object. Well, welcome to recursion, and welcome to all of the reasons why you should never use recursion if you don't absolutely have to. So, recursion is effectively when a function is self-contained inside of its definition, which means the function call is used inside of the definition of the function. This also means infinite loop. It keeps calling itself. You can think of like Inception, for example. Great movie, by the way. But Inception is usually the example I use to explain what recursion really is to people. So you might be wondering, this is useless, looks like a bug, why hasn't anyone done anything about this? Well, the reason being, recursion can actually be quite useful. It's sort of like, I guess, dark magic. You have to find the right way to use it. If not, it's gonna blow up in your face. But if you can master it, then your life will become a lot easier, because the way that you can do certain programs becomes a lot more streamlined. So what do I mean by this? Well, let's say, for example, we wanted to make this stop. Obviously, we don't want to use all of the memory that exists on our computer and possibly risk an explosion. So what can we actually do to make this stop? Well, we can have a base case. So how do we define what a base case is? I'll give you an example. Let's assume inside of do stuff, it takes in the value of an integer. Let's say in the start it takes in n, right? And then once it takes in n, then it first checks what n is. So if n is maybe equals to 0, right? Then stop the thing. Like for example, in this case, if n is equals to 0, then you could just return, because that's how you would end a function, return 0. You could just do that, or you can just write return on its own, because you're not returning anything in question for now. And yeah, if you want, you can write over here print we've reached the end exclamation mark. And then over here, instead of printing hello, what you can do is, if n is not equal to 0, which means that there's, whoops, wrong syntax, sorry, I just came up with a C++ tutorial. Old habits die hard. So yeah, if there is no 0, if n is not 0, then you have to call do stuff. But interestingly, you have to call it with n minus 1. What this means is that every single time you run n, the further calls reduce n by 1. Which means if you call do stuff for 9, do stuff 9, right? Then it'll go through everything, it'll realize, okay, it's not equal to 0, and it'll call do stuff 8, and then 7, and then 6, and then 5. And when it reaches do stuff 0, then you'll hear, oh wait, it is equal to 0. So we've reached the end, let's return everything, and life's good. So let's first let the computer understand this, and then let's put, for example, 5 in here. Well, in this case, it just says we've reached the end. And the reason behind this is because while it does all of these function calls, it doesn't say anything while it does these function calls. Let's make this a bit more illustrative. Before it calls the next function, it says, let's go again. And that followed by n is at, and then space, and then n. So if we do this, whoops, what have I made? Cannot concatenate. Oh, whoops, I forgot my typecasting. That's an embarrassing mistake. Yeah, if we run this, then see, it says, let's go again, n is at 5, n is at 4, n is at 3, n is at 2, and then n is at 1, and then we've reached the end. So how exactly does this recursive function work? Well, as you can see, first, when doStuff5 is called, then it looks. Is it n equal to 0? No, it's not. So it just prints out n is equal to 5, so let's go again, and then it calls doStuff4, and this process repeats and repeats until you reach the point where n is equal to 0. Then it doesn't do what's in the else condition, it just does this, which is printing we've reached the end and then returning. And by returning, you kind of bring yourself back to the previous reality in a sense. You kind of pull yourself back to the previous function, give it its answer that it was been looking for. And when you keep doing that enough times, you return back to your original starting doStuff5. So when you go down these levels, when you go from doStuff5 to calling doStuff4 to calling doStuff3, 2, and then 1, when you hit doStuff0, it tells doStuff1, yo, I've solved my case. And then doStuff1 is like, yo, I settled my side to like doStuff2. And then doStuff2 is like, I'm done here to doStuff3. And then it keeps telling the above function that called it that it's done, case settled. And then it manages to get everything out and finish the code. So that is effectively how you can use recursion to your favor. Now, there are a lot of algorithms that actually use recursion very frequently. For example, essential algorithms, if I go there, in essential algorithms, one moment, let this load, it's gonna take a moment. Let us go to quicksort, for example. In quicksort, if you would like to do iterative, this is the way you would do it. And nobody in their right mind would want to do this. In fact, it's every computing student's worst nightmare. But however, if you want to do it recursively, it's way simpler. And let's take a look at this. I'm not going to explain quicksort in a lot of depth today, but I will be going through the very basics of how the recursive calls kind of are used here, I guess. So over here, firstly, you have your base case. If the length of the array is less than or equal to 1, then you have to return the array back. This is your base case, the terminating condition. And then you construct your other ones based on what currently exists, and then perform the recursive quicksort on the specific smaller arrays that you've built out of the bigger array. So you are effectively creating your own arrays, doing quicksort on them, and then splitting those smaller arrays into smaller arrays, and then performing quicksort on them all the way down until you hit your base case. And when you hit your base case, you just return the value of the array. That is kind of why you're able to summarize it so well. And another example is merge sort. Let's look at merge sort. Merge sort algorithm, my god, my English is not Englishing today. Algorithmically makes a lot of sense, right? Because you're effectively just splitting it in half again and again and again, and then building it back up, as you can see over here with the merge function. But this is way easier done if you do it recursively, because while you do it iteratively, it is a bit more difficult. You have to merge them and split them in a slightly more different way. But when you do it recursively, your actual merge sort recursive code is just this. The actual merge function itself is just a helper function. Your code for the actual sorting algorithm is only 5 lines, which is your base case, creating mid, left, and right, and then just recursively merge sorting them and merging them together, which is pretty interesting, I would say. So yeah, that is the use of having these recursive algorithms, and you can see how they reduce the size of certain algorithms like bubble sort, for example, drastically. And again, recursive algorithms are only needed when it is genuinely simpler to do, because sometimes when you do recursive algorithms, you can end up costing a lot more memory, because one, recursive algorithms are not necessarily the most optimized ones, and two, recursive algorithms are also pretty prone to error if you don't code your terminating condition properly, which means that you will probably end up kind of screwing your computer over. So just be careful with that, I guess. So yeah, there's again examples for binary search recursive, which we have over here. Again, it saves a lot of time. You're literally just performing the same function on a smaller part of the original size. But one thing you have to keep in mind for a recursive function is that fundamentally, besides helper functions, like for example in merge sort, the actual input and output of all of the function calls must be the exact same. For example, if your binary search recursive has to be called on an array, a target, a left, and a right, no matter how you call it, it will have to take in an array, a target, a left, and something else. Like, you would have to use some sort of list, number, number, and number. List, number, number, and number. Just because you've declared it as list, number, number, and number. So that is one thing that you have to understand about recursive algorithms. Sure, there is technically a way to bypass this with default assignments to, I guess, parameters. That is technically something you can do. But for the most part, you will not generally be doing that. So yeah, linear search again. I didn't even know you could like do this, but there's this principle that I was taught by one of my seniors, which is if you can do it iteratively, you can do it recursively. And if you can do it recursively, you can also do it iteratively, which is scary for two reasons. One, because in an exam, for example, anything that is iterative and easy to code iteratively, they can ask you to do recursively. And like on the other side, anything that is too difficult to iteratively code can also be asked to be coded iteratively. Like if, for example, they ask you to code quick sort, right, or merge sort iteratively, you technically need to know how to do that. So yeah, just keep that in mind. And that's about all I have for you today. Recursion is really annoying. I'm gonna be honest, it is really, really annoying. And in most NOI like competitions I've went through, I've experienced a lot of I guess TLEs because of recursion errors. And I'm not gonna lie to you, like I am very, very bad at using recursion. But I would like to say that with practice, most people can get good. You just need to understand how not to get lost in the sauce. And very importantly, right, there's this thing called a trace tree and a trace table. Let me just Google this real quick. This is something that you gotta... What? Not this. This is something that you gotta learn. For example, when you want to kind of track what your recursive algorithm is doing, then you can kind of see what functions are being called, what return values are being sent, and how it works. So this is something you can do. And this is again for something linear like factorial. But there are going to be certain cases where, for example, in Fibonacci, where you're not going to have just one set of calls. So yeah, depending on how you draw it is going to depend on how you understand it and how the code works. But this is something you should probably consider doing. And importantly, you have trace tables as well. Trace tables are similar to trace trees. They're just slightly more difficult to see. It's kind of like logbooking what exactly your function is doing. It's a bit tough, but hey, it's useful, and whatever allows you to keep track of whatever's going on is good for you to do. So keep this in mind, have fun with recursion, and yeah, don't die.